Welcome to the Problems Channel Season 3, Episode 20, the episode which I titled A Finite Trigonometric Sum Evaluation, because in this episode we will do precisely that. We will find a way to evaluate a certain trigonometric sum, but before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the home page of our channel, and at the top of that page, in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. The best way to ask your question is to find an episode that is of interest to you and use the comment section under that episode. On my part, I will try to do my best in order to answer all of your questions. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and all the current supporters of our channel. The objective of the mathematical problem S3M11 is to find an alternative expression for a finite trigonometric sum whose common term has the following structure: 1 divided by the value of the trigonometric function of sine evaluated at the following argument: 2 raised to the power of k times alpha, where k is a whole positive number that varies between 1 and n, and being evidently another fixed whole positive number. And since in this particular case we have something divided by something, the divisor cannot be 0, and that means that all the arguments which turn the trigonometric function of sine into 0 are excluded, and these arguments are integral multiples of pi. So this is our restriction on the values of the real number alpha, which we will very promptly rename into x, because this is the most convenient designation, and that is what most students are used to. And this particular sum can be evaluated in a number of different ways. The sum can be evaluated using the machinery of synthetic plane Euclidean geometry, or the sum can be evaluated analytically. For demonstration purposes, I will evaluate this sum analytically, and I recommend that all of our viewers try to think on their own. How will they evaluate this sum using the machinery of synthetic plane Euclidean geometry? I will evaluate the given finite trigonometric sum using the so-called TAC, transform and conquer problem-solving approach. As such, if you do know how the transform and conquer problem-solving approach works, then you are in good shape. You will follow what is about to happen. And if you do not know how the transform and conquer problem solving approach works, then you are in luck, because on this channel we spent the entire season 1 and season 2 in a dedicated manner studying these problem solving approaches. So the transform and conquer problem solving approach on this channel is explained in all its glorious details across seasons 1, episodes 3, 4, 5, 6, and 7. And I also created a dedicated Transform and Conquer playlist on this channel. If you go to the home page, click on playlists, you will find the Transform and Conquer playlist, and click on that playlist. Look at all the episodes. It's not that much material, but it will be very, very helpful to you, because otherwise you may feel completely or somewhat or mostly lost in what is about to transpire. And what is about to transpire? Well, Remember the technical lessons of the transform and conquer problem solving approach were to take the original difficult or intractable problem and transform it into something or into a setting where we do gain a competitive advantage, where the transfer problem that preserves or keeps the technical essence of the original, because we do not want to solve some other problem, we want to solve the given problem, presents or becomes much more tractable. Once we solve the transformed problem, we reverse transform the solution, and voila, we solve the original difficult to solve problem. In this case, the transformation amounts to, and that was my idea when I was thinking about this problem, is to the differentiation. We make a brave assumption that this function, this finite trigonometric sum, can be represented as a function that in general depends on two variables, the value of the whole positive number and the argument x. I will switch the designations of the argument of our trigonometric function of sine to x. This is more pleasant and more traditional. Many students are used to that. So in our case, x is the real number such that 2k times x 2 raised to the power of k times x is not an integral multiple of pi. And at this point, we take the first derivative of both sides, the left side and the right side. On the right side, we have the first derivative of our function. I'll designate it with parenthesized notation, which is quite scalable. The second derivative will be just designated with parenthesized 2, the third derivative with parenthesized 3, and so on. Differentiation is carried out with respect to the variable x. And what do I have on the left-hand side? Well, in general, if this sum were infinite, we had to worry about uniform convergence and our ability to switch the order of the limits. This time the sum is finite. We do not need to worry about any of these technical details. We can just move the, let's say, differentiation operator through the summation sign, and instead of taking the derivative of the sum, we can take the derivative of the individual terms, which in this case comes out to what? The first derivative of the common term will have the minus sign. The trigonometric function of sine will live or percolate to the denominator in the second power. It will be sine squared. The same argument will remain. The first derivative of sine will be cosine, and the first derivative of the argument with respect to x will be what? It will be 2k. As such, what we have for the differentiated sum is the following: 2 raised to the power of k times the value of the trigonometric function of cosine evaluated at the same argument, 2 raised to the power of k times x. This is our result, and at this point, some of the viewers in the audience will say, Roman, what are you doing? If the original term, the original common term, was scary enough, now we obtained a sum, the common sum of which looks even more scarier. Well, remember the technical lessons of the transform and conquer problem solving approach. We claim that in the transformed setting, we will gain the competitive advantage. And what is the competitive advantage in this case? Well, I claim that the differentiated sum is telescopic. And here's the proof. Taking a closer look at the structure of the common term of the differentiated sum, we observe that when the value of the summation index k is 1, when k is equal to 1, then that structure becomes the following: 2 times cosine, the value of the trigonometric function of cosine evaluated at the argument 2x, divided by the value of the trigonometric function of sine squared evaluated at the argument 2x as well. What do we do over here? Well, here we do the maneuver that is usually carried out in integration when we want to reduce the power of the trigonometric function. So here we have 2. Still, we keep the factor of 2 for this ratio, and then we rewrite the cosine of twice the argument as follows: 2 times cosine squared of x minus 1 divided by, here we temporarily unzip the sign of the double argument using the famous double angle identity. So that will be 4 times sine squared of x times cosine squared of x. This is what we have. We simply unfolded the value of the trigonometric function of sine of double argument as the following product. 2 times the value of the trigonometric function of sine evaluated at the argument x, single copy, times the value of the trigonometric function of cosine evaluated at the single argument. Since the original is squared, the whole thing is squared, and this is the result. We will understand where that came from. And now what we do is we divide using this divisor to divide what we have in the numerator of that fraction. Now, when we divide the 2 times cosine squared of x term in the numerator, what do we have? 4 and 4 cancel out, cosine squared and cosine squared cancel each other out. So what do we have in the result? In the result, we will have 1. Remember, 4's cancel out, so we'll have just a straight up value of the trigonometric function of sine squared evaluated at the argument x, minus, here we carefully do the following. Here we zip this expression back in and we use the original denominator that we had when we started looking at the structure of the common term. So what do we have? We have 2 divided by the value of the trigonometric function of sine squared evaluated as the argument 2x. If you understood what just transpired, then you should be able to put this video on pause, walk away from the computer, and carry the solution of this problem all the way through to the glorious victory on your own and solve this problem correctly. Because now we enter the floss, rinse, repeat regime, and we realize that when the value of the summation index k becomes 2, all the relevant coefficients 2, 2, and 2 double in their size, but the overall structure and the relationship between the underlying terms remains exactly the same. The common term in this case becomes 4 times the cosine of the following argument, 4 times x. And that is what we have in the numerator. In the denominator, we still have the value of the trigonometric function of sine squared, but this time evaluated at the argument what? 4x. And then we unfold the value of the trigonometric function of cosine of double argument, still using the same reduction in power formula. We have 2 times cosine squared of 2x. Here we have 4x. Half of 4 is 2, so we have 2x minus 1. In the denominator, we have the same thing, but the argument of the trigonometric function of sine, in this case, double. Remember, it's not 2x as we had in the previous case, but now it's 4x still. It's double of something, and this is what we do here. We unroll it in the same way. Again, we use the same denominator to divide what we have in the numerator. The first division yields what? 4 and 4 cancel out. 2 remains. Cosine squared 2x, cosine squared 2x cancel each other out. What do I have? 2 over sine squared evaluated at what? 2x. And now recall what we had in the previous segment when k was equal to 1. This term was on the other side with the minus sign. So you already see the telescopicity in the works. And now we divide the -1 by the denominator. We collapse it back into the original. And what do we have over here? Over here, remember, the factor in front of the whole ratio was 2 raised to the second power. So 4 divided by the value of the trigonometric function of sine squared evaluated at the argument 4x. When the value of the summation index k becomes 3, then, as I mentioned before, structurally nothing changes in the relationship of the underlying trigonometric functions in this case, and the telescopic nature of the differentiated sum becomes more and more evident. That is, the structure of the common term when the value of the summation index k3 is the following: 2 raised to the third power, which is 8, times the cosine of 8x divided by the sine square of 8x. Same exact deal. We represent the cosine of double argument. And what is this case double? Well, 8 is double 4. So we have our cosine square of 4x minus 1, unzipped sine of twice the argument, which is again 8 is 2 times 4. So we have our representation of the argument is as follows: 2 raised to the second power, 4x and 4x. And again, as we divide the expression that we have in the numerator but by the denominator, we see that the following things transpire. There will be enough copies of 4 in the numerator in this case, and what will be left here is 2 raised to the second power. The cosine squared and cosine squared will cancel out. The sine square of 4x will percolate over here, so we'll have 4 divided by sine square of 4x. And what will we have for the second term? It will be minus. Well, here we have 2 raised to the third power. This is this minus 1, minus 8 over sine squared of 8x. And by now it is evident what exactly is going on with this differentiated sum. That is, if we carefully write down all the terms of the differentiated sum in their unzipped form, where each such term is represented as a difference of 2 functions, let's say, then we will observe the following. Most of the time we will write these consequent terms in a column, but because I do not have room on the board, I unzip them into one line, but it doesn't really matter. What matters here is that the structure of each and every summand of the differentiated sum comes out to be such that the second representation of the summand cancels out with the first representation of the first summand of the unzipped representation of the next one. In other words, this is our case when k was equal to 1. This is the case when k was equal to 2. This is the case when k was equal to 3. And look at what happens. The second summand of the unzipped first summand cancels out with the first summand of the unzipped version of the second summand. 2 over sine squared 2x with the minus sign, plus this term collides with the same term 2 over sine squared of 2x with the plus sign. So what happens here? Cancel and cancel. Likewise, 4 over sine square evaluated at the argument 4x with the negative sign collides with 4 over sine square evaluated at the argument 4x with the plus sign with the positive sign. Cancel and cancel. So will 8 over sine square of 8x will cancel out over there, and what will remain is the very last summand of the last summand and the first summand of the first summand of the differentiated sum. And we don't forget that we have the minus sign in front of it. This came from the first derivative of 1 over sine. Don't forget, so that's why I wrote negative 1 times this beautiful expression in parentheses, which telescopes in just 2 terms. And what are these 2 terms? Well, now once we take out negative 1 and bring it in, the first summand over here will be with the negative sign, minus 1 over the value of the trigonometric function of sine squared evaluated at the argument x, plus, because remember the last unzipped summand has the minus in front of it, minus times minus is plus, so plus 2 raised to the power of n over the value of the trigonometric function of sine squared evaluated at the argument 2 raised to the power of n times x. And this completes the proof that the differentiated sum is telescopic, the claim that I made earlier. And if you do not know what a telescopic sum is, then you are in luck again, because on this channel in season 3, episode 3, we precisely dedicate this episode to the explanation of what a telescopic sum is. Use the season guide for the season number 3. The link is in the comment section to this episode. Click on it, you will get to the free PDF file. There will be a link to season 3, episode 3, where we're explaining how telescopic sums work. But in general, for a moment, stepping from the fact that we have first derivative of this, telescopic that, regardless of all of that, if we abstract ourselves a little bit from the instantaneous tactical fighting that we're engaged in, from somewhat abstract perspective, what we have over here is yet another finite trigonometric sum. And in vacuum, we know an alternative expression for this here specific concrete finite trigonometric sum. And this is also in some way how the so-called tribal knowledge in mathematics is developed. The more we solve related problem, the higher the chances are that we will solve the next, perhaps more difficult related problem. And this is how we accumulate the overall knowledge. That's how we develop the nose and the gut for doing things in a particular vaguely defined layer of mathematics. So we'll chalk it up to yet another beautiful result, which we have in our bag. And what do we do now? Well, according to the transform and conquer problem solving approach, what we do now is we carry the reverse transformation. That is correct. Just one more time, in order to make sure that all the members in the audience are on the same page when it comes to the mechanics of the transform and conquer problem solving approach. Once we apply the transform and conquer problem solving approach to the process of recovering a solution to a difficult problem, and we manage to find a setting in which this original difficult to solve problem becomes more tractable, we manage to solve the transformed problem. How do we obtain the solution of the original problem? Well, we carry out the reverse transformation. And in this case, if we differentiated both sides of the equality that we established between the function of x and n on one side and the given finite trigonometric sum on the other, how do we undo the result of differentiation? That's right, we perform anti-differentiation, also known as integration. And it is interesting that many, let's say, direct operations in mathematics are quote unquote easy to carry out, by the converse operation is not that easy to carry out. For example, it is easy to add numbers, it is not that easy to subtract numbers. It is easy to multiply numbers, but it is not easy to divide numbers. It is easy to raise numbers to certain powers, but it is not easy to extract roots. Likewise, it is easy to differentiate in some sense, but integration is anything but. In this case, however, the integrals come out less than trivial. So if we take the integrals of both sides of our relation that is written over here, we skip the intermediate expression over here. The integral of the first derivative is the function itself, and here we integrate the expression shown on the right hand side of your screen term by term. Why? Because the sum is finite. Again, we do not need to worry about convergence of infinite sums, swapping the order of limits. This is all baby stuff. And on the right hand side of our relation, we have the integrals that are, like I said, less than trivial. Minus integral of 1 over sine square of x dx plus integral of 2 raised to the power of n over sine square evaluated at the argument 2 raised to the power of n times x dx. In some sense, this is how integral calculus can be born. We play with very simple differential equations, we try to integrate them, and boom, voila, this is precisely what happens. We develop the integral calculus. If you do not remember the antiderivatives of these functions, then in general, you should remember the following u over v rule. This is u prime times v minus u times v prime divided by v squared. This is what we have. So if we take, for example, let's say if we take our favorite trigonometric function of cotangent, which can be represented as the ratio of cosine of x times sine of x. Then we differentiate over x, differentiate this whole thing over x using the rule that I just said. The first derivative of cosine is negative sine times sine is negative sine squared of x minus cosine of x times the first derivative of the denominator, cosine. This becomes a square divided by sine square of x minus 1 factored out. So this becomes negative 1 over sine squared of x. In some sense, this is, if anything else, you just remember, like I said, that one rule that comes in handy even in integration, and we will see that on this channel several times. But for now, we just skip right to the end, so to speak, and we write down the following result. Our function Sn of x, that was the sum k of 1 to n 1 over sine 2 raised to the power of kx, becomes what? In this case, it becomes cotangent of x. Here it becomes what? Negative sine minus 2 raised to the power n. We move under the differential. It doesn't make any difference. And then we have essentially the same integral. Minus cotangent of 2 to the power of n times x plus a constant of integration. In this case, we combine two constants of integration produced by each indefinite integral into one. And now our final task is to recover the value of the constant of integration c. How do we recover the value of the constant of integration c? Well, by its nature, it's something that is present in that sum at all times, and the value of that constant or the value of that something does not depend on the number of terms in the sum, as long as the sum is evidently present. As such, putting the upper summation boundary n to 1, we have 1 divided by the value of the trigonometric function of sine evaluated at the argument 2x must be equal to, let's spell it out, cosine of x divided by sine of x minus cosine of 2x divided by sine of 2x plus c. And what do we have over here? In the denominator on the left-hand side of the equal sign, we have the trigonometric function of sine evaluated at the argument 2x, 1x, 2x. 2x is missing. How do we manufacture 2x over here? Well, we divide by 2 times the cosine of x and multiply by 2 cosine of x. So over here we will have 2 cosine of x squared, and here we'll have sine of 2x. Game over. And from here it follows that for the value of the trigonometric, for the value of the constant of integration c, we will move this term over with the positive sign. Cosine of 2x divided by sine of 2x. And then what do we have here? We'll have plus we will have this term right here, 1 over sine over 2x, minus this term, minus 2 times cosine squared of x divided by sine of 2x. And what do we call 1 minus 2 times cosine square of x? Well, this beautiful mess over here becomes minus cosine of 2x. Would you agree? And here we have same term but with the plus sign. Plus sign, well, let's be diligent over here and neat. Sine over 2x, this is our mess right here. So minus cosine of 2x over sine plus cosine 2x over sine. What does that mean? That means that this whole expression is equal to 0, and the constant of integration, the value is recovered, and that value is 0. Now that we showed that the value of the constant of integration c is 0, we solved the problem completely, and we now know, or we can claim, that an alternative expression for the given finite trigonometric sum can be the following: the difference between the values of the trigonometric function of cotangent evaluated at the argument of x and evaluated at the argument 2 raised to the power of n times x. And since we're dealing with trigonometry in general, we know that just about any trigonometric function or any trigonometric expansion can have a gazillion of different variations. One such variation is shown over here in the middle. We can represent the same trigonometric function of cotangent as 1 divided by tangent of x, where tan is, again, the trigonometric function of tangent, minus 1 divided by the value of the trigonometric function of tangent evaluated at the argument 2 to the power of n times x. This is yet another alternative expression for the given finite trigonometric sum. And some members in the audience can say, how did Roman, that's me, how did Roman know which steps to take and where to go? Well, the answer is, Roman, that's me, I did not know that these steps will solve the problem. All I had to do is try, and while trying, that's what I found. And in that sense, nobody knows. And that means that when we set our eyes upon any worthy mathematical problem, we do not know upfront or ahead of time whether this problem has a solution at all, and if it does, how many different solutions does it have. And this precisely shows, I hope, one more time, that mathematics is an art. Mathematics is an art of telling a story, and in order to tell that story, we need to exhibit and showcase our creativity, ingenuity, and improvisational skills, and this is precisely what we do on this channel. Our next challenge will be a problem in mathematics, S3E20, and the objective or the challenge of this problem is to find a notion in physics. I underline the word physics because this is precisely how we want you to solve this problem. Not a combinatorial argument, however beautiful that argument may be, not some other analytic manipulation, but it has to be a notion from physics that will evaluate the following binomial sum. The structure of the common summand over here is the following: k, the summation index, times the value of the binomial coefficient, and choose k. K varies, n is fixed, n is whole positive number. K in this case varies from 0 to n, but this is just a minor detail. If you want to have it, you can roll this sum starting from k equal to 1, evidently because when k equals 0, the first term evaporates. But this is a hint for you in order to help you figure out which notion in physics will evaluate this sum. And at this point, you should really walk away from your computer. And if you still need a hint, then this hint comes in the form of the following question. In mathematics, when we multiply something by something, this coefficient k, what is the alternative name in mathematics for that coefficient? Exactly. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my solution of the mathematical problem S3E20.